last session. So actually, well, my name is Anne Wendel from VDMA, and it's my pleasure to be here with you, and also to the followers at home, welcome. Actually, the first presentation now is a continuation of the last session. So Oyvind Theie, who drove down from Oslo.
That's right.
That's right, exactly. So he is going to talk about unleashing the potential on arm-mounted 3D vision robotics. So Oyvind from Civit, happy to have you here, and the floor is yours.
Thank you. And I have to give a shout out to Wim. So who was one of, I was very happy to see that someone could make use of some of the content that we had on our webpage in the previous presentation. So that was nice. Yeah, so I'm Oyvind, and I lead, I'm head of products in Civit. And today in my presentation, I'm going to take you through a little thought experiment on how to maybe look at the 3D vision applications in a slightly new architectural light. So we have this very interesting picture here. It's a car, and the 30,000 components that goes into building this car. And you can see there's all kinds of shapes and sizes and materials and whatnot. And I think a lot of you guys and also others here in Stuttgart this week are contributing with 3D vision applications to help manufacture cars like this and also thousands of other products. And in addition to seeing just a bunch of objects here, I'm also seeing, as a product manager in a 3D camera company, I'm seeing an ocean of challenges. This is a lot of difficult and hard stuff. And I also know that a lot of others here see the same as me. And the reason is, every day we get customers in our doors, and they take one of those parts, they bring it in their hands, and they come to us and say, hey, can you please take a picture of this with your 3D camera, and begging and praying and hoping that it works for their application. Sometimes it does, and sometimes it doesn't. So let's just go on a little bit experiment and assume that some customer, maybe the Volkswagen here, comes and asks someone to say, OK, can you please build me a robot that can pick these washers somewhere here, pick them out of a bin, and feed them into a machine. So, OK. Easy, you think. That's fine. So we start with some robot and an appropriate gripper. We have the bin, and we put the camera above the bin, and we start taking images and picking. So this is all fine, pretty simple. And you start picking, and then you have 10 parts left, 5 parts left, 4, 3, 2, and 1. And then there's one image, or one part, that you just can't get out of that bin. And then you're like, OK, well, what happened there? So you take a look at the point cloud. And you find that there's no 3D data left. So what we have here is what we call an optical singularity. It's a piece of area where basically this component is rendered impossible to image given the current state of the conditions. Like with this camera, with this angle, with this light, whatever, it is impossible to take a picture of this. So you call in an operator to fix the machine and keep going. And you think that's fine. But this will happen again and again and again and again, if not every bin, maybe many times per bin. So this becomes a problem. So you need to do something. Something has to change. And there's actually a quite straightforward way. What we need to do is we need to look at this singularity look at this optical singularity from a different angle. So we basically, you could add another camera from a slightly different angle, looking at it. You could add 2, or you could add 3. Maybe you put it all in a big, fat frame, and it looks quite nice. And it offers now 4 angles to look at this, and you're doing quite good. Well, basically, this is a quite common approach used by many vendors, and it's a very sound one. And it's doing quite good. You get more 3D data, and that's nice. But there's a backside of it, of course, because you're just pouring money into solving a problem which has a diminishing return. You don't get infinitely or twice as good data if you add another camera. You get slightly better data. So imagine that we want to have infinite number of viewpoints and that are correlated with the robot. So instead of using this big-ass frame with, with very many cameras and expensive system, we just put the camera on the robot. Basically, if you think about how we humans operate when we look around, it's pretty much the same thing. If I'm getting blinded by these lights, I can simply sort of look away, or if I want to see what's happening on the backside of this stall, I can go around it, and that's fine. And why shouldn't robots do the same? I think they should. So take an example here. On the upper left corner, it's a picture taken from a stationary point of view with a 3D camera, and we are looking at the 2D camera from this sensor. And what we have inside is a black anodized L-shaped piece of metal. It looks kind of like my phone. Same sort of optical criteria or characteristics. It's actually a horrible item to take a picture of. And it's basically invisible from above. You have a little bit of sparse data here. If I was designing a 3D vision system and I needed to know how to pick this thing in order to feed it into a machine, I would not really know how to pick it. It's like, should I take it right on there? Should I take it on the sides? What do I do? So there's a lot of ambiguity with this part. So instead, we just put the camera on the robot. We're free from the shackles of doing stationary cameras. And simply what we do is we take the camera, we look a little bit to the left and a little bit to the right. And we put those things together, and all of a sudden, this very strange part becomes possible. Now we know how to pick it, and we can feed it into the machine, no problem. And you can imagine if you have objects like this, which there were quite a lot of in the picture with the car, this thing will happen all the time. So this offers quite an interesting way of dealing with that problem without resolving to an infinite amount of cameras that you put around. So what we get is we avoid singularities. Because we can put the camera a little bit closer to where it wants to work, we also get better resolution. We get less noise. We get higher accuracy. We get less ambient light disturbance. And this is because if light hits a certain object from one angle, looking at it from a different angle, you might mitigate that problem. And you also mitigate some artifacts like reflections and whatnot. So instead of tailoring your on-arm bin picking solution to sort of the worst case performance, you could instead tailor it for the best case performance for that sensor. And that gives you higher performance stability and also more margins. So this is quite cool, but it's not the end of the on-arm story. There's also other things that opens up when we put the camera on the robot. For example, if you want to serve multiple bins, like in flow racks or shelves and whatnot, you simply can move the robot to see where it is. So with the same camera, we can cover 2 stations, 4 stations, 8 stations. It's fine, and you don't need to rack up a stationary camera for every bin that you're looking at. And it also opens up the possibility of doing what we call, or having self-contained cells. So basically, what we get here is, instead of having multiple cameras to calibrate and install and whatnot, you just have one. There's one camera to maintain, and it also frees you up from using a lot of scaffolding to put up these systems, and you save space, and you save some money, and you free up the robot movement. So this is actually very nice from an integrator point of view, and sort of serving the robot cell after it's been sort of given life. And as this picture shows, it's also essential for mobile manipulators in the future of in the factory of future. So, sounds all nice and fine, but we get some questions. You know, it's too slow. The cycle time when you do put the camera on the robot, it's too low. And programming the robot is very complex. You need a motion planner. The camera is too big and heavy. it's difficult to maneuver, and it kills the payload. And what about the camera? Can it really handle all of this stuff? What about all these vibrations and accelerations and whatnot? So we thought a lot about these things, which is why we here in Civid came up with Civid 2. So basically, we want to usher this era of on-arm applications with this camera. It's not the end goal, but it's the start of sort of that transition. And it's been purposefully designed with on-arm challenge in mind. So it's very small, it's lightweight, it's really fast, can take a 3D image in full HD with color in 100 milliseconds. It's very accurate. We have accessories to put it on the robot, and it provides both color and 3D. And it is rugged and industrialized. So even though you move it around, different temperatures, whatnot, it will do the same thing every time. There's an example of a point cloud that's taken with this camera. It's 2.3 megapixels, wide dynamic range, and it's provided in 100 milliseconds. So this is starting to look quite interesting. But still, it's natural to say, but still, I mean, the concept of putting that camera on the robot is still going to slow my application down. And yeah, I would say it depends. But to say that it can't reach acceptable cycle times is kind of debatable. Because one thing is for certain, and that is cycle times can be pushed very far if you apply a little bit of ingenuity, and smart solutions can be fast solutions. So basically what we did is we took 3 ways of using the camera and we compared them. So we took a stationary system with this Yaskawa GP180 robot, and we did a bin picking solution where we were picking from this place and dropping it pretty much behind the robot. And we did the same with the camera mounted on the robot, but in that case we also tried, what if you take an image before you go in to pick it, but also you could say, what if I take an image after I have removed the part? We call those entry imaging and exit imaging. And then we also looked at what happens if you use a little bit of memory here. So you take a point cloud and then you identify maybe 2 pickable objects. So you take 1 pick, and you take another pick, and then you take a new picture. And then you take 1 pick and 2 picks, and then another picture. And you can add this on. So we basically then looked at how this pans out. On the left side, we have the cycle time in seconds. And on the right side, we have the penalty in time in percentages. And when we start looking at this, you see, of course, stationary cameras in this case can be quite fast because you can image while the robot is doing some other job. But because the 3D camera is also very fast, and it has a field of view which allows it to take images not too far away, the added cycle time, if you go in for a new image every pick, in this case is 1.5 seconds and 2.5 seconds. Added on to 5 seconds. Okay, it's not as fast, but still, it's not that bad either. Many applications that we see out there are like 9 seconds or 12 seconds and whatnot, and this is quite achievable. Now, if you add a little bit of smartness, so you say, okay, I'm going to take this picture and I'm going to pick on the left side of the bin and then on the right side of the bin, assuming that the integrity of the position of those parts are contained, well, then this penalty is sliced in half. So we go from 40% and 60% time penalty down to 20 and 30. Okay, it's starting to look interesting. And then you can keep doing this a little bit. Maybe you can do 3 picks per image or 4. And all of a sudden, we're talking like a second or less of time differences. So this is starting to look kind of interesting. And then if you take into account the fact that you will have a higher picking success rate, given sort of the added optical redundancy we did just because we put the camera on the robot in the first place, this is actually starting to look quite attractive. So I think that's pretty much what I wanted to give with this slide, where it's sort of like, yes, this is the beginning. This is what we can do actually today. And imagine going down the road 2-3 years from now, this will look even more impressive. So it's a very cool journey that we're starting on here. So in conclusion, this on-arm 3D camera strategy, it opens up kind of a new page. Some are using it a little bit, but it will happen a lot more. And basically, you can move that robot to see more, and you can move that robot to see a little bit better. And your robot cells are granted sort of a new level of flexibility and freedom if you go with this kind of approach. So on that note, I hope you got some inspiration and some new ideas for growth and exploration in your 3D applications. We here in Civid, we will charge onwards and lay the foundation for tomorrow's 3D vision applications. That's what we're going to do. And I'm betting a good bottle of champagne that many of those applications out there in the future will have a camera on that robot. That's for certain. So thank you. And as always, if you can see more, you can do more.
Thank you, Oyvind. So thank you. That's quite a revolution, so to speak, isn't it?
It's I think it's like yeah. I mean, you have to think a little bit differently. It's not. It's not. Yeah, you just open your mind a bit. I think that's it.
Interesting. So you mentioned you showed us two pictures, isn't it? On the left-hand side, how the performance is on Roboterarm installed versus stationary machine vision system.
Mindestabstand von 1,5 Metern zu einer Person ist einzuhalten. Sie sind verpflichtet, eine medizinische Mund-Nasen-Bedeckung zu tragen. Wir folgen die Gebote derzeit gültigen Corona-Verordnung. Dear sirs and madams, due to the current COVID-19 situation, please note the general hygiene rules. A minimum distance of 1.5 meters from people must be observed.
Is that it?
Follow the requirements of the currently valid corona ordinance.
Huh.
Okay, so now we know.
Okay.
So the question is, you honestly mentioned that for the time being, the stationary scanner is succeeding, but there's a great potential in the future. So what would be the first application that you see your system working on?
Yeah, so I mean, it depends a little bit on what you want to achieve, and I think these in manufacturing, where you really care a lot about sort of high quality picks or whatever you would like to call it, you need to know accurately that you do the right job every time. I really think that this on-arm strategy is very viable already today. There's many times, I think, as we saw in the very beginning of the examples, that a stationary setup would fail a lot. And on a production line, that is maybe completely unacceptable. You don't want downtime on this thing. So from that perspective, I think it's actually a very viable solution already today. While in some like emerging logistic applications where or like fast order fulfillments is everything, and you don't really care if you break well, you do really care if you break a box or whatnot, but I still think that they kind of measure a lot on speed in that application. I think there still needs to be a little bit more maturity, but it's going to get there as well. Okay. So it's kind of like if you want to have as few errors as possible, I really think this on-arm approach can be like order of magnitude better. While on the speed front, you might drop off a little bit. So you have to trade those two. But in manufacturing, there's already a lot of applications that could be solved doing this approach,
so a lot of
assembly
potential.
and so on.
A lot of potential. Thank you.